Thanks everybody for coming. This presentation is kind of has two related focuses. The first is spatial, and the second is temporal, which is implemented in a way using some of the spatial stuff. So that's why it's all related to the same talk here. So I'm going to start by talking about the spatial stuff, and then I'll get into some of the more temporal things. This is kind of the agenda here, representing work that's happened over the past year maybe, or less. A bit about me. I'm a freelancer full-time now. Since March, I've been doing freelancing a little bit more before that, but now it's full-time. I also wrote the first solar book, and I'm a Lucene committer, PMC member. The third edition is still being worked on. It's very, very close. I'm hoping for the end of December. And I'm sorry if you've already pre-purchased it. You may have pre-purchased it a couple years ago, perhaps. It is coming, and it is very, very close. Only one chapter is in a draft status, so just progress is happening. So before we get into some of these specific spatial things, I think we need to talk about an overview of what's going on within the Lucene spatial module. And a key point here is that with spatial, there's multiple ways to actually technically implement requirements that are based on different uses. So there's a key abstraction here called the spatial strategy, and it has maybe half a dozen different subclasses. And the most prominent one is, the most versatile, is our recursive prefix tree strategy, which I just say RPT for short. It's kind of a mouthful, to be honest. And it's basically a grid-based. I just want to highlight this particular one a little bit more. We'll get into it a little bit more. But a key point here is that there's a shape abstraction that has no other dependencies, really. So the shapes are, the shapes implement being a shape, whether it's a rectangle or a circle. And then the prefix tree strategy in particular communicates, it knows about shapes and works with them. And the other spatial strategies work with the shape layer as well. And the prefix tree strategy is a grid-based strategy, and it has another abstraction called the spatial prefix tree, which actually implements a particular grid of some nature. So there's a geohash one, there's a quad one. The geohash one is really only for geodesics, but the quad one can handle other numeric data that may not be, spatial on the Earth. And a bit more about the shape layer. That's actually implemented in another open source library called Spatial4J, which in turn uses something called JTS for polygons. Many people don't even need polygons, and that won't be a factor. But if you are using polygons within Lucene and Solar, and sometimes Elasticsearch, then you're indirectly also using JTS for some of that capability. And the prefix tree strategy, it kind of wraps things up together, and depending on the different spatial predicates you have, whether it's intersects, contains, within, disjoint, each of those has a different body of code that actually searches the grids. And they tend to reuse a fair amount of code, and those talk to the prefix tree. Another thing I want to point out here is that the prefix tree, these are fairly well decoupled, so you can introduce a new shape and change nothing else. You can introduce a new prefix tree, and the intersects, contains, and within all basically work, and I'll tell you more about that. So when it comes to indexing point data using this recursive grid technique, it's very scalable. It works great. Here's an example here of using some point in Boston, where the geohash encoding of that is DRT2Y. Obviously, if I wanted to get more specific, I could start adding more letters. Every letter refers to a grid square, so the very top level on the globe is divided into 32 cells. One of them is D, and then next down from there, et cetera. You keep recursively going down until you get as much precision as you want. So to index a point to about a meter precision, you're talking I think it's like 11 different terms. And But a polygon, or basically any shape other than a point, is a region. Or even a line, it covers a bunch of grid squares. So if I were to take Massachusetts, there's a lot of grid squares for that detail, and that does not go down to a meter. That goes to, I forget what precision it is, but there's 508 cells there. So it's not, so points scale very well with this technique, but polygons and other non-point data, there's really a balance you're trading off here between how accurate do you want this thing to be and how much space are we going to need to do it, because it's exponential. So for more accuracy with point data, you just need to go down to another level. That ends up being just one more index term on disk, no big deal. You can keep going and adding more levels. But for other shapes, no, it's exponential. You really have to have a threshold there. So there's a little, an important configuration parameter in the Solar schema when you actually use this through Solar called the dist error %. And that basically says if you were to take your shape, which might not be a circle, but if you were to take its approximate radius, and by default it takes 2.5% of that radius, and it says, well, if I can fit a grid square, the biggest grid square I can fit in with there, I'm going to stop at that point. I'm not going to go down. I'm not going to go to any more than that. And that is a big, how small you make dist error % is a big difference on how accurate it is. So by default, this kind of short circuits generating a ridiculous number of terms that the system can't handle if you were to give it a polygon for any region of decent size. And you tend to get about a few thousand, but with the default, you tend to get about a few thousand terms or so. You can definitely change that. So if you have requirements that call for much more accuracy, if you're giving polygons to Solar, then that says that you have an actual geometry, a vector geometry of the region of interest. So what some people have done is basically use the existing features within Lucene from either Solar or Elasticsearch, and then they'll do a double check on their end against the geometry. But that's kind of expensive to do on that end. So with this new spatial strategy here called serialized DV strategy, and it's named that way because it's the serialized geometry, and it's in doc values, hence the DV in the name. And that's binary doc values is an efficient place to put a chunk of data. And basically the binary, a fairly efficient encoding of the vector geometry is in binary doc values there. And it's as accurate as the polygon you give it. And it's important to know that this thing is not an index. You can't use this thing by itself because you can only look up the value on a per document basis. If you want to know what's in a certain region, you marry this strategy with the existing RPT index and then use it together. I have a code sample on the next slide. There's a lot more potential here. Well, obviously there's a missing Solar and Elasticsearch level kind of adapter for it. And there's a lot more potential too, because if you think about it, if you look at, if I were to go back, just to some of these grid squares, like there's some large grid cells within the middle of that polygon. If you were to match something in the middle of, if that happened to be your query shape, then you know that everything on those inside grid squares, you know you've completely matched it. You don't need to double check it against the geometry. So that insight is not yet leveraged, so there's a great deal of potential there to have really fast and accuracy together. It's one of the things I'm excited about in the future. Okay, right. Here's some sample code from another presentation given at FOSS4G that I attended. The people I work with to bring serialized DV strategy, the Climate Corp, they put a presentation together and threw some sample code to show how easy it is to use. And it really is, at the Lucene layer, it really is pretty easy. With the spatial strategy, you get with the RPT grid, you get a Lucene query. You do it again for the serialized geometry, and you put them together using what's called a filtered query. But you configure it to make sure that the serialized check always happens last, because that's the second pass accuracy check. And with this kind of approach, you can also, like you might, without serialized geometry, you might be tempted to have more accuracy in your grids than you actually need. Because with this, you might back up on the number of cells you need to index a given polygon, knowing that you can always get the accuracy in the vector geometry. So it's pretty nice. So I worked with the Google Summer of Code program with a student in India named Varun Shenoy. And he successfully built a new prefix tree choice. So to date, there's been the quad and the geohash choices. This is a much more flexible one. You may have, if you've searched through Jira before, you may have noticed one that has the word Hilbert curve in the title. This implementation does not actually have Hilbert curves yet. As we were digging into it, it was far more, I mean, it'd be nice if it had Hilbert curve ordering of the data, but I think what was far more impactful was being able to actually configurably choose how many subcells are at each level. So the problem with the quad and the geohash one, I shouldn't say the problem, but I mean, it's fixed, you know, so the geohash one has 32 subcells at each level. And the quad has 4 at each level. So the quad one tends to have large indices, the geohash smaller. And you know, for performance reasons, it's actually better to have the top grid cells in the world don't buy you that much. It's not much point in having few big ones. So you want as many as possible at the very, very top. And towards the middle, you want a small number so that you can you get more accurate, you get more precision that way. You can more quickly find out how many cells you need. And once you get to the very, very bottom, the search algorithm does a fast scan. So the cells don't buy you anything at the low level. So you want you don't want lots of levels at the bottom. Basically, this allows you to configure, say, 256, 64, 16, 4, 4, 4, 4, 4, 4, 16, 256. You can kind of flow the cells like that, and you get better performance. And you can more configurably trade off your index size with search, basically. And your mileage definitely varies on search performance. You know, sometimes it only seemed like it was 10%, but on my machine with a certain setup, you know, I saw 100% increase in filtering performance with the benchmarking. So I'm pretty impressed with that. Now there's another spatial strategy that it's kind of been around for a while actually in Lucene trunk. And this summer I revamped it and brought it over into the 4x line. And this is all about indexing rectangles. And the main point of using this one really is, I'd say, the area overlap relevancy. Because if you're indexing a bunch of, I've seen GIS apps where there's different layers. You might not even have a ton of layers, but you have layers that have certain spatial interest in the world. And if you're looking in a certain area, there might be a spatial region that just barely clips your screen that the user's looking at. And that's arguably not a highly relevant relation to your query window. On the other hand, if you get something front and center right in the middle and it covers most of your search area, that's a highly relevant kind of match. So this computes, the formula's out on the screen, but it basically computes the relative overlap between an index rectangle and your query rectangle to try and figure out what are the better matches. And that's in Solar as well as bounding box field. Here's the schema set up to use it. It's very easy to use. You generally use doc values with it, and you can use the standard bounding box syntax if you want. But if you want the other predicates like contains or within, then you would use the syntax down here. And this is where you get the overlap ratio choice. You also have a couple other ones too. Like if you just simply want the indexed area ordered, you could do that. So I've worked with, over the past year, I've worked with 5 different kind of interns and students on this related code base, whether it's Lucene Spatial or whether it's Spatial for J, which is tightly related. The 3 middle ones, not all of these are finished. The 3 middle ones are works in progress. I think it's not a coincidence that they are the geodesic ones, because that stuff is hard, and especially geodetic polygons. I've only heard of one implementation out there, and I've been encouraging Raytheon to open source it. And they just recently gave me the code, but I'm looking for them to officially put it on GitHub or something like that. That'll be something else when that's available. Yeah, cool. So that's the first part of my presentation about the geospatial kind of subjects. Somewhat recently, I've been looking at using the same kind of infrastructure in the spatial module for some date times use cases. And it just doesn't actually it's not strictly about date and time, actually. Let me back up a second. It can apply to numeric ranges of other things as well. It's just that whenever I see a good use case, it tends to be the date-oriented ones. But understand, it's general. And if you're indexing just a single date value or multiple date values for Lucene or Solar Elasticsearch, then the existing stuff works fine. This doesn't necessarily really replace that. It's especially for durations. And by duration, I mean, you have a start time and an end time. And you want to index that, and you want to search via ranges as well. So I remember a long time ago, I was working with some SQL databases and other things, and it's pretty typical, very straightforward to understand that you could simply approach this with a start time field and an end time field, and then depending on the nature of your query, whether it's any kind of overlapping or whether it's a contains or within, you can basically come up with a couple different range queries against the start time field and the end time field in a very straightforward way. In fact, someone asked this question on the LinkedIn Lucene group, and it's not even Lucene-centric at that question. It's a very straightforward, has a generic kind of solution. But it is single-valued only. In other words, if your document has only one range that you're trying to represent, then no problem, it's cool. But if you have a variable number of ranges, then this doesn't work, because even though Lucene has multi-valued fields, the values aren't really coordinated across fields. It's theoretically possible, but it would be a ton of work to try to fix that aspect of it. This is not really the right solution if you have multi-value duration data. How many of you have seen this picture before, by the way? I'm just curious. I Okay. So this was really kind of fun, kind of open source engagement where I was on the mailing list and Jan, I'm not sure if I said his name right. He said, yeah, I bet this time duration problem, maybe this spatial logic could fix it. And I started thinking about I think he's onto something. And I started back of the napkin calculations of grid boxes. I'm like, hold on here. There's a solution here. And then once I described what the queries looked like, then Haas looked at it and was like, this is amazing. And he drew this wonderful picture that I love and I reuse. And he did a meetup on it. So that was pretty cool. The idea here, for those that are not familiar, is that you express a duration in an XY space as the X is the start time and the Y is the end time. So all the data fits above the line. Those colors on the side is just the legends. Don't be confused by that. And depending on your query, you have a different rectangle query in this space. So this reuses all the spatial prefix tree logic completely. It's just an application of it. And there's a wiki page on the bottom. If today you have this problem, if this is totally valid solution. The wiki page shows some details on how exactly to configure it. I think it's very cool. It's a little bit of a hack. But nonetheless, I still like it. The aspects of it that aren't really perfectly clean is that, well, it'd be really nice if it was wrapped up in a bow with a nice, easy-to-use wrapper, so that you can just give it, your range query and not have to worry about the details of the floating point spatial kind of stuff. And there's some floating point conversion because the spatial module the APIs were built around floating point data, not integral types like integer and long. And if you use the quad prefix tree, you only have the bits in the mantissa of a double to use, not the full 64 bits that'll say any millisecond the value that you might get back. So there's some issues to work around there, but those are solvable. I still like this. Yeah. So there's another approach I developed recently, which is to create so in the spatial module, is to create a single-dimensional prefix tree. And because of the decoupling in the API between the search side, I mean the intersects, contains, within, all that search logic that typically goes against geohash cells or quad cells can be reused 100% without any modification whatsoever. So I started this by building the core of the capability is generic, and it's called a number range prefix tree. And it has a configurable number of levels per, a configurable number of cells per level. And there's only one subclass right now, and that's the date range prefix tree that says that, basically it makes sure that years get their same level and all months get the same level. It actually aligns with useful ranges that are meaningful to most applications and users. And it's not just for ranges, by the way. I mean, this came about because of the requirements for ranges, but if you had dates that you wanted to search, then this can work as well. I'd love to find out how fast or slow it is relative to plain old tridate. I've not benchmarked it. I don't know. Theoretically, it should be a lot faster for a couple reasons. I think I may be getting ahead of myself with that. So it reuses a lot of code. And so at the very top level of the tree, you have the million years, and I think in a long, it ends up being like there's like 200 and something odd million year intervals. And then you have the million years, then the 1,000 years, and then years, months, days, hours, minutes, seconds, milliseconds. So when you index a range, this was really developed predicated on the fact that you're going to give it ranges that are typically not random milliseconds and whatever BC to AD. It's typically going to be something meaningful like a day or some number of months or some number of seconds or stuff of that nature. If the ranges are, as I just kind of suggested, I'm calling those common date ranges, then the number of index terms is, it could vary. It could be only 5 or 6 if it's exactly 1 month, say. It could be more like 10 or 12. It could be upwards of 50 once you get into some odd day to some odd day in another month. But if you're choosing random milliseconds, totally randomly, it ends up being the absolute worst case is about 14,000, which is a lot. But that's not what this is for. And if you're indexing one-time instant, you're always getting 9 terms, or less if you need it to a second precision or month or et cetera. And so just as for indexing, when I say how many terms it takes for these kinds of typical ranges, the query side reflects of the same nature. So if your queries are typically not random millisecond ranges, if they're like, I want to say everything within a certain given year, that ends up being very, very fast. That ends up being like, basically a term lookup. Ends up being it's every parent as well, so it ends up being 5 terms or something like that. But it's extremely fast for that. The previous mechanism does have one upside functionally, and that is if your different values per document is variable and they overlap and that's pertinent in some way, then the previous mechanism keeps that distinct. Whereas with this approach, it sort of gets coalesced. So in other words, if your document has a range that says, like all of the year 2012, but you had another range that said a certain month within 2012, it effectively becomes the same thing as all of 2012. So that may or may not be relevant to your requirements. Now, just to make a comparison to the try, if you index a standard date field in Solr, that translates to a numeric field, which uses conceptually similar ideas, but even the tridate field using a long, it has something called a precision step. Most people don't mess with it. The default is precision step of, I think, 6 for dates, which means that you have 2 to the 6th power number of levels on down, and that's not, those levels don't align with meaningful date boundaries. It's arbitrary. So a typical query on a try field is going to cover 640 some odd possible what I call cells, but terms. Whereas, compare that to 10 or 20 or 50 or something like that. It's a factor of 10. So the point is that even if you don't have ranges, you could use this, and it's theoretically faster. I have not benchmarked it. The use case driving this is ranges. And it's actually an example coming up soon, which is really, truly driving this further. So this is in Lucene 5, and 5 is not released yet, but it's coming out in a month or 2. And it has a Solr field type to make it easy to use. You have a field using it, you have the field type, I happen to name it the same. And you could give it time instances just like you might do for a date field. It doesn't handle the date math right now. There's definitely some nice to haves that you could theoretically make it better. Like it'd be nice to say, I never need seconds on down. I don't. It'd be nice to also say, that I don't care about millennias. Like those levels don't buy me anything. It'd be nice, but right now you always get the full 9 levels. So it's possible to be fully compatible with the full possibilities of range of date values that you ever might get. So here we see a range, and the syntax is pretty straightforward. If you want something other than intersects predicate, then you have to use the syntax on the bottom where you can say contains. So it's very easy to use. Now, let's say we want to facet on date values. There's a picture, a kind of a motivating example, seeing this, and as it was proposed to me, as how can we make this fast? And this screen where this comes from, it goes on and on. There's like, I forget if there's like 3,000 some odd little cells. I think it's like a decade worth of values per year. That's a lot of values. Now, and this is one way of visualizing this. Of course, another way is obviously doing a standard bar chart. Same data. So Solar's got date faceting. That's not going to handle the date range case, which is motivating for me to do most of this work. But it's also generating, it's internally, whenever you give a date range query to Solar and you get back, say, 10 values, because you get 10 adjacent bars, each of those values was a separate little internal query. It's also cached and gets put on a bit set and put on the heap. That doesn't really scale very well unless you're reusing lots of those intervals. Then there's the new to Solar 4.10 is the facet.interval technique. It also doesn't handle ranges. It's not for that. It requires doc values, and it's not implemented in the same way. It doesn't have the same characteristics as the kind of plain old facet.range. So it should be much more scalable. But I needed to also make something that handles date ranges. So right now it's a work in progress. Faceting on the date range field stuff I was just describing. Internally, looking back, like each of those boxes translates to one term that I need to count. So that really lends itself to I should be able to generate the data for this sub-second, no problem. I have no idea what the thresholds will turn out to actually be once actually implemented, but it's not. But the state range field, the index structure totally lends itself to being able to power these really rapidly. And the cool thing about as I've started to write the code for it, it reuses a lot of stuff I've already done. So like I already have a tree walking visitor and all that stuff. I just need to change what I'm doing. Instead of filtering, I'm counting. I just need to put the count in the right bucket and increment it. So far I'm really liking how it's turning out so far. Now, there's always trade-offs. So this makes sense when you're faceting on date ranges like months and days and typical common ones. It's not for arbitrary or variable changing possible things. The code should be able to be amenable to support that hypothetically, but it's not really intended for that. And I'd love to see a benchmark at some point of these things. Now, future stuff I'm excited about. I'm excited about everything I was just talking about, but there's other things I'm excited about. So there's some works in progress I highlighted, like the flex prefix tree I think is awesome. I just need to bring it up to speed with trunk, kind of run all tests for an entire day on the thing just to make sure that no failures trip and get that committed. If you take the same example before where we're doing date faceting, take that same approach but do it to 2D data, and it should reuse a lot of the same concepts where you're basically iterating over the terms and counting them, but instead of putting it into one big range of date intervals, you're putting it into a 2D grid of numbers where each cell is counted and incremented. So that's, I'll be doing that in January, for real. And something I am really excited about is something that Michael McCandless is working on with, I think Adrian Grand had the idea, and I think this is just absolutely fascinating, is the idea of auto-prefixing terms. So within spatial, the spatial grid technique, and with the numeric data, when you index it with the precision step, you're configuring where you want bigger cells to be, parent cells. You're actually forcing that to happen, and so you're explicitly creating terms at a fixed grid. What the auto-prefixing is going to do You don't have to auto-prefix anything. So in other words, let's say I have a geohash. I just need to index it at the full 11 character, the precision that I need. I don't need to generate all the parents. And under the covers, it will internally figure out that, geez, you got a lot of data in New York City, but you don't have like anything over the North Pole. So instead of generating a bunch of terms on the North Pole, I'm not going to do that. I'm only going to do it where there's a concentration of data. And so what that's led to, it's questionable whether that's going to make it to Lucene 5, because it's kind of like an API change in an underlying way. But I think that's kind of phenomenal, because it's basically leading to smaller indices for this data. This stuff can use a lot of space on disk. And there's definitely more prefix tree optimizations to be had, especially when you're indexing ranges or polygons and things. I think the point case is pretty well optimized. There's some stuff to be done, but yeah, especially leaves get indexed twice, which is really, the spatial indices over polygons are really 40% larger than they need to be. That's it, and thank you very much for coming, and I'll take questions. So. What kind of heat map will I support? There's a geohash grid aggregation feature. Mm-hmm. All these three are going to be supported also with Solar? No, those are specific Elasticsearch things. And one of the things on my plate is just to look in to see what they're doing more. I think they're basically faceting on the cells, but I don't think they. I don't know, but I don't think they're actually iterating over the actual terms and counting it in that kind of efficient manner. So I believe that if my intuition is right about how they're doing it, I believe that that's going to lead to being able to show heat maps like this of a high precision of thousands of cells, I think, in a much more faster way than another approach would take, if my understanding of how Elasticsearch is doing it is right. Aishna? Have you considered weeks? Weeks? Which doesn't align so well with yeah. Yeah, that's a good point. I thought about it as I was working on it. I think, how do I do this? I don't know. And I kind of just sort of dusted it under the covers for now. Yeah, I think that if the date range stuff, my initial implementation is going to be very simple, where if there's one term for that value, I count it that way. But I should be able to say, I should be able to know where the week boundaries are and simply count all the days that are for that same week. That should be able to work. But I don't think that's going to work the first time. So I don't think I would change the index over that requirement. Yeah, cool. Any other questions? Cool. Well, thank you very much for coming. I really appreciate it.